So as I just said, we're going to be covering section 8.4 today over trigonometric substitutions. And really what we're going to do today is find some creative ways to apply the Pythagorean theorem. So let me just write down the version of the Pythagorean theorem that we're going to be using this morning. Really, it's two versions. So the first one, probably the most common way to write it, sine squared of theta plus cosine squared of theta is equal to 1. And then the other common way to write it when you divide through everywhere by cosine is this, 1 plus tangent squared of theta is equal to secant squared of theta. But what we're going to do today, we're going to want to add on an extra constant multiple. So what I want to do is take both of these equations and multiply both sides by a squared. So this isn't a huge change, but it will help us in a few minutes when we're looking for substitutions to do. So I multiply by a constant a squared everywhere and just distribute it through. And the same for the other equation. You would get a squared plus a squared tangent squared equals a squared secant squared. And you'll see the reason for this constant in the example, just below here. Maybe I'll put a note here that we multiply by a squared Okay, so this is the integral that we want to do first. We're going to look at 1 over the square root of 9 plus x squared. Okay, so we know quite a bit of calculus at this point, so we should think through the kinds of techniques that we know about and just see if there's one that's relevant. The first technique that comes to mind for an integral that looks like this would probably be a u substitution of some sort, and probably you would pick u equals 9 plus x squared, and then du would be 2x dx. So the u is fine, but when you try to look for your du in your integrand, you're going to be out of luck. So a u substitution won't work, and neither will any of the other rules that we've learned. This one might look a little bit like one of the inverse trig functions or inverse hyperbolic functions, so maybe one of those could come in handy. That's possible. But really what we want to do is something a little bit new. What I want to do is to use this formula, and yeah, I pointed to the correct one, this one here, to help me solve this equation. So you might be wondering, there are trig functions here, no trig functions here. So what I'm actually going to do is have to substitute a trig function in, add a trig function to this in order to use that. So we're going to make it look more complicated in order to actually do the integral. So what I'm going to do is compare this to this formula here. Maybe I'll box these since they're important. So underneath the square root here, I have a number plus x squared. And in the second formula, I do have a number plus tangent squared. So this is going to be my hint that this is the proper formula. The second one is going to be the proper version of the Pythagorean theorem to use to do this integral. And in order to deal with this 9, this 3 squared, I want to make sure it occurs on every term in my formula so that this actually works out nicely. So what I'm going to do is substitute in x equals tangent theta, but I'm going to add on an extra constant so that it matches this one. I'm going to add 3, so that when I square it, I'll get a 9 tangent squared of theta. But anytime we're doing a substitution in an integral, we have to also worry about dx here, the differential. So dx in this case will have to take a derivative of 3 tangent theta. That'll give us a 3 secant squared of theta. And then I should tag on a d theta to get my new differential here. So let's substitute in and see how this actually worked out. So dx becomes this, the 3 secant squared. And underneath my square root, I'll now have a 9 plus x squared. So that'll give me 9 tangent squared of theta. So comparing this expression underneath the square root to this formula from the Pythagorean theorem, we have 9 plus 9 tangent squared of theta. So this we'll be able to substitute in and simplify the 9 secant squared of theta. So we're going to use formula 2. Okay, so this is a little messy. Let's go ahead and come down below here and rewrite things. Underneath the square root, we now have a 9 secant squared. Okay. And then up top, we have 3 secant squared. And now we have to take the square root to simplify the expression a little bit further. Remember, when you take a square root of a square, you actually pick up an absolute value, though we'll see that this doesn't really affect anything, the absolute value. So we get a 3, and then an absolute value of secant. So it looks like we're in much better shape now. So here, since we do have this absolute value, I should make a note here that as long as we stick between minus pi over 2 and positive pi over 2, then secant is going to be greater than 0. So let's make this little assumption here. In most of your problems on your homework, you don't really need to worry about this sort of thing. It's just a little technical detail that I need to mention here in lecture. So we can drop the absolute values. That's the point here. And really, if we go back to the original expression, we have 1 over a square root. We know that this is always going to be positive, so we really don't have to worry about any negative numbers here either. This is the second half of my point here. So theta needs to be restricted between minus pi over 2 and positive pi over 2 because our original expression is always going to be positive anyway. So when we get rid of the absolute value signs, we can actually just cancel. And the only thing left in our integral at this point is just a secant. Secant theta d theta. And this particular function, we do have a rule for. It's actually a natural logarithm of the absolute value of secant theta plus tangent theta. So this is an integral. I don't know if we did this one as an example in class, but it was certainly in the section on the natural logarithm way back in chapter 7. And it's in the table of integral formulas. What was it? Table 8.1 that I pointed out the other day with all those formulas that you should probably have memorized or at least be very familiar with. Okay, so it looks like we're done. We don't have an integral anymore, but there's one issue. In our original integral problem, we had x's. And in our result down here, we have thetas. So we need to do a little bit of work to substitute something back in for theta in order to figure out what it is in terms of x. Okay, and this is the point where it gets possibly a little bit tricky. We have to think about how to convert back to x's using what's called a reference triangle. So maybe over here in this little, we won't be able to see this. Over here in this little corner, we'll talk about reference triangles. And this is something similar to what we talked about in chapter 7 when we tried to calculate inverse trig functions and that sort of thing. Let's see. Pen is not cooperating this morning. So what we're going to do is look at this expression, tangent theta and then just move this 3 to the other side. And we have to remember that tangent is really, if we're looking at a triangle, something like the opposite side over the adjacent side. So let's draw a triangle where the angle theta is opposite a length x So here's theta down here. So opposite x and adjacent side would be 3. And then since we know two sides of our triangle here, we can use the Pythagorean theorem to find the third side, since this is a right triangle. So remember, a squared plus b squared equals c squared. For this particular triangle, it would be x squared plus 3 squared is equal to c squared, where the c is the hypotenuse of our right triangle. So if you took the square root of both sides, you would see that the third side, the hypotenuse of our triangle, is x squared, the square root of x squared plus 9. And once we draw this reference triangle, we can now find secant of theta and tangent of theta. I guess we already know tangent of theta is x over 3, but we will need it for secant theta. Maybe down here below my triangle, I'll remind you that secant theta remember, is 1 over cosine, or the hypotenuse over the adjacent side of our right triangle there. So we're going to look at the hypotenuse, the square root of x squared plus 9, over the adjacent side 3 when we take secant of theta. And this will let us get our final answer. So secant theta, like I just mentioned, becomes the square root of x squared plus 9, and then over 3. And then tangent theta, we can either remember as x over 3, or we can look at the opposite over the adjacent side in the triangle, x over 3. It's the same answer either way. Okay. And that's how you do it. That's how you get rid of theta.
Ollie.
Let's see. Not sure what's going on with whoever's microphone was on, but please remember to keep it muted unless you have a question, so that you don't get apparently random exclamations coming through. Something exciting. Okay, so are there any questions over this process or this idea of reference triangles? Okay, so maybe I'll just draw a little arrow here, just to remind you that on this step, we had to draw the reference triangle in order to get rid of theta. Okay, so no questions, really? Really no questions? Then let's get this out of the way and do a second problem here. So now we're going to integrate a slightly more complicated function. This guy. And we are going to do this one again with a trig substitution. So we should go back to the two formulas, the two Pythagorean theorem formulas that we looked at earlier, and figure out which one is going to be applicable in this situation. So will it be this one or this one? And looking at this particular integral, the thing that we're going to try to simplify is underneath the square root. So we're looking at a constant minus something squared. And we need to see which of these formulas would help. Where can we get a constant minus something squared? And in this one, we can get a constant plus something squared. That doesn't seem like it's going to be helpful. This is the formula that we used in the last example. But if we look at this one, if we move, let's say, this a squared sine squared term to the right, we'll have a constant minus something squared. So this first formula is the one that we're going to use in this particular problem. So we're going to do a sign substitution. And once you do a few examples, you'll get the hang of how to figure out which one to use just by looking at these formulas. You just have to figure out which one will be helpful in this particular situation. Okay, so we know we want to end up with a constant minus something squared, a sine squared, but we would like that constant to match up, this 4, to match up with a 4 sine squared. And the only way to do that, or the best way to do that, is like this. So I know I want to end up with a 4 and then a sine, but I need to somehow, get rid of the 9. And let me just try this again. Make it a little bit cleaner. Okay, so in order to end up with a 4 after we square, we'll have to write a 2. But in order to cancel off the 9, we'll have to divide through by 3. Okay, so squaring this fraction will give us a 4 over 9. The 4 we want to match up with this constant, and the division by 9 will cancel off this one. And then dx, we just need to take the derivative of sine to get a cosine theta, d theta. Okay, so let's do this substitution and see if it simplified things for us. So maybe we'll write out all of it this time and not try to do any simplification in this first step. So x squared becomes 2 over 3 sine theta squared. And that's all underneath the square root. And then x becomes 2/3 sine theta. And then dx becomes 2/3 cosine theta. And we need a d theta now, since we have a new variable. Okay, so once again, on this first step of substitution, it looks like we made things way worse than they were. But we'll see in just a second that it will simplify down to something much easier to integrate. So we have some constants that we can pull out. Let's get started there. We have 2 copies of 2 over 3, so we can pull out a 4 over 9 from our integral. And then we can't really do anything with sine or cosine yet, so we'll just copy those down. Underneath the square root sign, we can do the simplification that I was talking about earlier. When we square 2/3, we get 4 over 9. So the 9 cancels. Leaving us with this, 4 minus 4 sine squared underneath our square root. And this guy here is what's going to become our cosine. Our cosine squared. So remember, we moved this to the right side of the equation, or at least we mentally did it, and then you're left with the a squared cosine squared. On the other side, so now underneath our square root, we have 4 cosine squared theta. Let's see, and maybe over here, I need to add a little bit of a technical detail. This is, again, not something that I expect you guys to worry about on your homework. This should be a less than symbol. But this is something that I do want to mention in lecture. Really, we need to think about restricting theta between minus pi over 2 and positive pi over 2, same as the last time, in fact, because we want to make sure that we get all the possible values of x, but we don't have to repeat those values. So thinking about what x can be here. And remembering that as you go around the unit circle, you repeat values of sine and cosine. That's why we made this little restriction. Again, not something I expect you to worry about on the homework. Let's see, and there is a question there. How did you take the 4 out of the square root? Are you talking about this 4 here, Cameron? Here? Moving this 4 out? Okay, so this 4 actually didn't come from the square root. It came from these fractions here. So we had 2/3 times 2/3, which when you multiply becomes 4 over 9. And I just moved that constant to the front of the integral. Yeah, good question. But now we can actually get this 4 out of the square root. We just take the square root of 4 and get a 2. And my point, what I was trying to get at with this technical detail, is that cosine in this region is always positive. So when we take the square root, we don't have to worry about adding an absolute value symbol. We can just write cosine theta. Like I said, a small technical detail that lets us get rid of an absolute value. Because now it cancels. Our cosines cancel. And our integral at this point is much simpler. We have another constant that we can move to the outside, this 1/2. So we have 2 over 9, and then inside the only thing that's left is a sine function. We have a sine theta d theta. Okay, so we did a lot of work with trig functions in order to simplify our integral down into a single sine function. We know the antiderivative for sine is negative cosine. So we get minus 2 over 9 cosine theta plus c. Okay, but now we have the same kind of problem, the same kind of issue that we ran into in the last one, where we have thetas in our answer, but we really need it in terms of x. So let's think about this guy here and make a reference triangle. Let's see, adjust this so that we can see everything important. So remember, x is equal to 2/3 sine theta. So if we multiply through by 3 over 2, we can get sine theta by itself. And we can see that sine theta is equal to 3x over 2. So I'm just rearranging this expression here. But this lets me draw the reference triangle. So we draw a right triangle with an angle theta. This is how I like to draw mine. It doesn't matter exactly where you put theta. You could put it up here, or you could rotate your triangle however you want. Just be consistent. But we know that sine theta is the opposite side length over the hypotenuse side length. So the numerator becomes the opposite. The denominator becomes the hypotenuse. And then we can solve for the missing side using the Pythagorean theorem. In this case, maybe we're solving for b instead of c. So 3x squared plus b squared equals the hypotenuse squared. And then just solve for b. We'll see that it's equal to the square root of 4 minus 9x squared. If you just multiply everything out here, maybe go ahead and just label that on your triangle. Like so. Okay, so we needed this side length because we're going to do a cosine. Remember, cosine is the adjacent side. Let's make a note down here. Little reminder, it's the adjacent side length over the length of the hypotenuse. So we'll need this square root of 4 minus 9x squared when we do cosine of theta. Okay. And then the hypotenuse we know was 2, so that'll go in the denominator. And then always remember to bring your constant down when you're doing an indefinite integral. So this is the answer for the second example. Okay, any questions over that process? Okay, so there's a question, is the missing side of the reference triangle always going to be the bottom of the starting fraction? Let's see, the starting fraction, I guess you mean the integral here. Yes, so the bottom of this fraction did turn out to be the hypotenuse. Excuse me, it was not the hypotenuse in this side. In this case, this turned out to be the adjacent side of our triangle. And no, it's not always going to work out that way, but it does often work out that one of these pieces of your integral will match up with a side on the reference triangle. See, I guess in this particular example, that was the missing side. And it was the bottom of our fraction that we started with on that one. That's really, I guess, coincidence. Though it does often work out that way in practice. So any other questions before we do our third example? So if you were paying close attention to the last two examples, we actually didn't need to do this technique. We could have done that last one using a U substitution, I believe. And then the first example, we could have used one of the hyperbolic functions that we have an integral formula for in order to maybe do these a little bit faster. But sometimes you actually will run across an integral that there is no other way to do, like this one, which looks similar to the last problem. Okay, so on the last one, I said that we could have done a U substitution. That's because we had an X in the top of our fraction, but now the X is in the bottom, so even that won't work. This we really do have to do a trig substitution for. And in this case, we're going to do a secant substitution. So you might notice that we've done 3 different kinds of substitutions. This is the third one. In our 3 different examples. And we're doing a secant in this one because if we look at our formula here and compare it to the problem, we have x squared minus 1. And if we move this 1 to the right side, we'll have a tangent squared of theta equals secant squared of theta minus 1. So that's going to be the reason why we use this one. So x is going to be secant. Which makes dx tangent times secant, the derivative of secant, and then d theta. Okay, so underneath the square root here, we now have a secant squared, since we're substituting in a secant for x, secant squared minus 1. And then x becomes another secant in the denominator. And then dx we have to worry about here becomes a tangent times a secant d theta. Okay, so once again, it looks like we made things worse than they were, but maybe you already can see some cancellation. The secant from the denominator will actually cancel with the secant over here. So right away we can start simplifying. And then underneath the square root, we can go ahead and substitute back in our tangent squared using the Pythagorean theorem. And I don't even need a fraction anymore. Don't know why I write it that way. So we have a square root of tangent squared, and then another tangent theta d theta. So the square root of tangent squared should really be an absolute value of the tangent, but since we're multiplying by another tangent anyway, we can just write it as a tangent squared. This is always going to be positive. So what do we do with tangent squareds? We learned this in the last section. When we have even powers of tangent, we have to convert them into secants. So we're actually going to kind of undo what we did to get the tangent squared underneath. We're going to go backwards to secant squared minus 1 in place of tangent squared. So the reason why we do this is we don't have an integral for tangent squared, but we do know one for secant squared. That's just tangent. And then minus 1, we'll get a minus theta, and then plus c to finish off. Okay, so we're nearly at the end. We know at this point, having done a few examples, that we'll need to come up with a reference triangle in order to get rid of theta. Okay, so remember x is equal to secant theta. So in our reference triangle, we'll use that to make our side lengths. Go ahead and write down some of this. And secant theta is equal to x. But remember, I want to think about this as a fraction, as the hypotenuse over the adjacent side in this case. So I'm going to write it as x over 1. Okay, so here's my triangle. I'll fill in the hypotenuse, the adjacent side, and then we can use the Pythagorean theorem to solve for the other one. We don't have very much time, so I'll just go ahead and tell you what it is. This will end up being x squared minus 1 underneath the square root, which in this case was actually the top of our fraction that we started with, if you're following along. Okay, so here's our reference triangle. We need to take tangent of this one. And remember, tangent is opposite over adjacent. So we're going to look at the square root of x squared minus 1 over 1. And dividing by 1 doesn't do anything. So we'll just write the square root. The theta will have to do something a little bit different in order to solve for. So remember, x is equal to, maybe I'll just write it down again. X is equal to secant theta. So if I do secant theta inverse of both sides, we can solve for secant inverse of both sides. We can solve for theta. So just use the inverse function here. And that gives us theta. So we actually have a minus secant inverse or arcsecant of x in our answer. And that's where we can stop, finally. That'll be our solution. Okay, and that takes us right to the end of class. So good timing. So if there aren't any more questions, I will see you guys tomorrow morning. If you do have questions that you want to ask, please stick around for a few minutes and I will try to get to those. Your homework for this section is already posted. It's the due date is set to Friday. So please make sure you take a look at those problems. And if you run into trouble, please make sure you ask questions in class or go seek tutoring if you prefer to do it that way. But these problems are getting kind of tricky, especially when you have to draw these reference triangles. So please make sure you start early so that you give yourself the best chance to complete the homework before it's due.